This is a recording for notes for 4.6 graphs of other trigonometric functions. One thing I just want to say right away is keep in mind that the original period of sine and cosine were both 2 pi. So when we were dealing with b and the period, we were always taking 2 pi divided by b, which is the new period. And now we'll find that some other functions don't have 2 pi as the period. So moving along, graphs of other trigonometric functions. We want to be able to sketch graphs of tangent, cotangent, secant, and cosecant, and then also graphs of damped trigonometric functions. So starting along, we'll have the graph of the tangent function. And just like with sine and cosine, we want to have a good picture of just a plain old tangent function in our notes. So we know that the tangent function is odd, and that is the tangent of negative x equals the negative tangent of x. So just a little, reminder of that the tangent of negative x is equal to the negative tangent of x. And so this graph of y equals tangent x is symmetric with respect to the origin. So think about that. That means that if we turn it 180 degrees, it maps onto itself around the origin. And we also know that tangent x is equal to sine x over cosine x. And I'm actually just going to write that here. Tangent x equals sine x over cosine x. And so because of that, that means it is undefined when the cosine of x is equal to 0. And so when does that happen? That happens when x is equal to negative pi over 2, and then pi over 2, and then 3 pi over 2, and increments of that. So think about if we take the smallest or the first positive value that it's undefined at, that's pi over 2. And then think about what you keep adding here as you go on in this pattern, and you're adding pi. You're adding pi, or 2 pi over 2. For that common denominator. So we're going to say that gives us then that the tangent of x is undefined when x is equal to pi over 2, pi over 2 plus n pi, and plus n pi, or sometimes I say pi n, and so I'll use this, or x is equal to pi over 2 plus pi n. So since we're going in increments of pi, that means then that the period, since it's repeating every pi, and n is an integer, just I should have maybe written that, but let me write this first. So that means that the period of tangent x is pi in this case, and I should have added here where n is an integer. N is an integer. So just kind of keep that in mind as we go. And then we're going to think about our table of values. And remember, when we make our table, and here's a different table, but maybe I'll go back to this page. And when we do our big table, and tangent is down here, and there's sine theta, cosine theta, degrees and radians. And I didn't really want to make the whole table, but maybe I just will. 0, 30, 45, 60, and 90 are the angles in degrees. 0, pi over 6, pi over 4, pi over 3, and pi over 2. 0, 1/2, square root of 2 over 2, square root of 3 over 2. Oh gosh, square root of 3 over 2, and 1, 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. And then tangent, that's what we want to think about now. It's 0, the square root of 3 over 3, 1, the square root of 3, and undefined. So in this little set, if we were going to plot those, and I'm going to go forwards and backwards, the ones that I would say I'd plot are this one, and that one, because, you know, I don't necessarily know right off the top of my head what the other ones are. So if I think about that, this is pi over 4, and this is pi over 2. And so let's even go backwards, negative pi over 4 and negative pi over 2. And so the key points that we have here at 0, it's 0. At pi over 4, it's 1. We'll just say 1 is there. And at pi over 2, it's undefined. And then at negative pi over 2, it's also going to be undefined. We had said that earlier. And then at negative pi over 4, it'll be at negative 1 there. Positive 1 and negative 1. And so then we get this tangent function, and those are asymptotes as we look at those and go through that. So this just shows you the table of values, you know, using decimals and things like that. And so let's do a nice graph of y equals tangent x, and we'll kind of put some things on here. I want my 4 cubby holes, and so I'm going to do that same thing. I'm just going to put 1 period. This will be negative pi over 2, negative pi over 4, 0, pi over 2, and pi over 4. I'll go 2 boxes to make 1 and negative 1. I have this handy little asymptote there. I was so proud of myself when I figured out how to do that. But nice little infinite cloner at pi. Oh, I see I wrote my fractions incorrectly. This is pi over 4, and that one is pi over 2. My apologies there. And then our values at negative pi over 4, we're at negative 1. At 0, we're 0. At pi over 4, we're at 1. And what this looks like, oh, I didn't keep going straight there. It looks like this. And those are asymptotes. So that's 1 period. So really, if I just kind of clone that graph and kept looking and going, it would make that same thing happen. So some things we maybe want to remind ourselves of. First of all students take calculus, and so notice if we do have an angle that goes up that way, tangent is positive, but an angle that goes down that way, tangent is negative. So that's how we kind of can remind ourselves that that's what's happening there. This one is symmetric with respect to the origin. If we turned it upside down, it would match itself. So we'll write that symmetric with respect to the origin. In this situation, remember what amplitude was? It kind of gave us that maximum and minimum. Since this goes to positive infinity and negative infinity, the amplitude is considered undefined. Even if we have a multiplier in front of our tangent x, if we have, you know, I'll say 10 here, so instead of being at 1, it would be at 10. That just is going to stretch it, but it is not considered an amplitude, just like when we multiply, you know, x squared and have 2x squared, it stretches that graph, but we don't call it an amplitude as we go. So we're going to say amplitude is not defined. Amplitude is not defined. And for tangent, we're going to have 5 key things, but we're going to have the 5 key things are going to be only 3 points, these 3 points right here, and then the asymptotes. And the asymptotes kind of are at the ends of that. Notice we still are using that kind of 4 cubbyhole concept as well. And so here's some other things then that we want to be able to say about this. So we're going to use 3 key points and 2 asymptotes to graph. And the asymptotes, remember we kind of said that in that last one, they're at pi over 2, and then they go increments of 1 pi after that plus pi. And so we're going to write that just like we did before, and we're going to say that these asymptotes are at, and maybe I'll write it in green because that's what I was just writing in. These asymptotes are at x equals pi over 2 plus, and the book authors say n pi, so I will as well. And that's where these asymptotes are as we look at that. And in this case, for our key points for the first period here, they're at the beginning and the end of the period. So in this case, they're at x equals pi over 2 and x equals negative pi over 2. And x equals 0 when y equals 0. So those are the asymptotes, and then our key points are 0, 0, and then in this particular instance, it's pi over 4 comma 1 and negative pi over 4 comma negative 1. And that is, just for this plain situation that we have right here. The next thing we want to remember, and is very important, is that the period, notice that space that we've graphed, that single period, the period is pi. So before, when we used the period is 2 pi over b, now for or tangent and cotangent, the period will be pi divided by b. It is not continuous. It has infinite discontinuity at pi over 2 and then increments of pi thereafter. So for this one, the domain is the set of all x such that x does not equal pi over 2 plus n pi. And then we want to say several things. X is an element of the real numbers, and n is an element of z. N is an element of z, which is the integers as we go. But then our range, because think about this, it's going down to negative infinity there and then up to positive infinity. So our range is just from negative infinity to infinity as we go. And just a reminder, I'll just write it over here, that z is integers, set of integers, just to kind of remind ourselves of that. And then I have some other things here as we look at this, and we'll just kind of make sure that we have written everything. Here's kind of a picture, and this one has more than one period. We gave the period domain. We said that the asymptotes are at x equals pi over 2 and negative pi over 2, and that's the beginning and end of the period. Asymptotes symmetric with respect to the origin. I think we said that as well. Yes. And since its period is pi, we want to just be aware of the fact that the asymptotes are at pi over 2 and then intervals of pi. The domain, we've already talked about that. And when we sketch this, it's similar to the way we had looked at key points before, but now we'll have 2 asymptotes and some key points as well. So remember that the asymptotes are at the beginning at the beginning and the end of the period. And so when we kind of think about this general form, and it's kind of written again there, we don't have the D added on, but that's okay. That you want to write this down. The asymptotes are going to be when this bx minus c is equal to negative pi over 2, and when bx minus c is equal to pi over 2. That will give you, you know, those two key parts, which are the two asymptotes on the edges. Right in the middle of those two is the x-intercept, and then kind of halfway in between the x-intercept and the asymptote, or the asymptote and the x-intercept, it's either positive or negative 1, so to speak, as we go. So these are the asymptotes, at beginning and end of the period, beginning and end of the period. And so we want to, if we can just set that bx minus c equal to negative 2 pi and then equal to positive 2 pi, we can find those endpoints. This just reminds us amplitude is undefined, is not defined. Asymptotes and the x-intercept, if you want to plot additional points, you can. And then sketch one cycle, and then you can sketch things to the left and to the right. Okay, let's look at one and kind of graph it as we go. If you feel like you want to graph this yourself and then check my work, by all means, go ahead, and I will just get started on it here. And so y equals the tangent of x over 2. Just a reminder, that's the same as y equals the tangent of 1/2 x. So kind of keep in mind then that that means that this b is equal to 1/2. And so the next thing we're going to find is the beginning and the end of the period. Find beginning and end of the cycle, we'll call it cycle. And so to find that, we're going to take this, which is just 1/2 x, and we're going to set it equal to negative pi over 2, and we're going to set it equal to positive pi over 2, and kind of see what we get for those endpoints as we go. So we're going to say x over 2 equals negative pi over 2, and that's where it begins. And that'll be an asymptote, and it ends when x over 2 is equal to positive pi over 2. So in each case, to solve, we're going to just multiply by 2 on both sides. And actually, I'm going to kind of do them both at the same time. In this case, it's the same work. So x equals negative pi for the beginning, and x equals pi for the end. So these are there are asymptotes. Asymptotes at x equals negative pi. Let me write that a little better. And x equals pi. And you know, we want to stay with our kind of 4 cubbyhole thing. So I would then say, since I'm going to negative pi and positive pi, I'll just go negative pi and positive pi. That will give me my 4 little cubby holes there. So I'll mark them, but I'm just going to write in the pi's. I'm going to draw 1 period, and then I'm going to draw more periods just to kind of see what that looks like. So let's pull in some asymptotes. So there's an asymptote, and here is an asymptote. Oh, just kidding. That wasn't what I wanted to do. Oh, there we go. So I've got my asymptotes on there, and then I'm just going to remind myself that halfway between those two, right in the middle, it's at 0, and then in this case at negative pi over 2, it's at negative 1, And at positive pi over 2, it's at positive 1. And I didn't mark that on the axis, but this will be 1 and this will be negative 1. And then I just sketch that in. Oh, and my drawing is just not super great tonight. And then I'm going to draw maybe 3 more periods. I'm going to draw another one. No, I'll draw 2 more periods. I'll draw one to the left and one to the right. That'll be nice. And I keep grabbing the wrong thing here. There we go. And now remember I used 4 boxes. So 1, 2, 3, 4. There's my next asymptote. And I could label my axes. So here's 2 pi and 3 pi. And then, oops, pi to 3 pi. And then here's negative 2 pi and negative 3 pi. There we go. And so then there's going to be another asymptote. Oops, I forgot to grab it with this. That's 4 away there. And we didn't really say what the period was. I'll go back and do that as well. And then my key points, halfway, it's at 0 and 0. And then it's at 1 there. Negative 1 or negative 1 and 1. I have a little thicker marker right now. And here we go. Oh, that's not good. Oh my goodness. My drawing is not very well done. There we go. I'll just darken that one up a little bit more. So there are 3 periods of that. And if we wanted to find the period, remember the period this time is going to be pi over b. And b is 1/2, so that's pi over 1/2. I'll invert and multiply. So that's pi times 2 over 1, or 2 pi. And notice that the distance from negative pi to positive pi, that's 1 pi, 2 pi. So that has a period of 2 pi as we go. And make sure that you can find your 4 or 5 key things. So we had 2 key asymptotes and 3 points in the, I'll quote middle, in the middle, those 3 points that we find as we go. So if you did it yourself, I hope you did well. Let's look at the next one. And now we're going to sketch the graph of y equals negative 3 tangent 2x. So y equals negative 3 tangent 2x. Now, a couple things are happening here. So the negative, it's reflected across the x-axis. So reflect across the x-axis. So, I'm going to go back to this previous problem and say if we reflect that, it would go like this. So we would have this, the opposite places. 0 is still going to be 0, but it'll just, the asymptotes will be the same, but it will reflect across the x-axis. And then the 3 part, it's not called the amplitude, but it still will stretch it by a factor of 3 vertically. So that's a vertical stretch by a factor of 3. And then this 2 means it's going to have a period. So it's going twice as fast, so it'll be half as long. The period is going to equal 2 pi over, or excuse me, just pi over b. Whoops. Pi over b. B is 2, so pi over 2. And so we want our 4 cubby holes again. So, and it's not moving it left, right, or up, down. So I'm going to call these 2 points. Well, let's see where the beginning and the end are. I know, but I guess I haven't said that yet. So the beginning asymptote will be when 2x equals negative pi over 2, because that's the original, and it'll end when 2x equals pi over 2. When we then multiply each side by 1/2, it's the easiest way to do that, I think. Then we get x equals negative pi over 4. And then same thing here, except x equals positive pi over 4 as we go there. And so what we're going to do is we want our 4 cubby holes still, and we're going to start at negative pi over 4. And we're going to end at positive pi over 4. And think of that, that's a fourth of a pi and a fourth of a pi. So that would be a half of a pi, and our period is a half a pi. As we, oops, pi over 4, I lost that. And now it is going to have that stretch. So I'm going to go 1, 2, 3. 1, oops, 2, 3. I could have maybe gone by 1 box, 1, 2, 3, but I didn't. Negative 1, negative 2, negative 3, 0, 1, 2, 3. So now let's kind of think about that. We've got everything in there. I'll put our asymptotes on the ends of one period. And so there's one of them at pi over 4. Oops. Here's the other one. Just a second. There we go. And now the 0 point is still at 0, so that's not going to change for us. But remember, it's reflected. So instead of, in this one, instead of being negative there, it's going to be positive. And instead of being at 1, it's going to be at 3. And same thing here, and this is like pi over 8, just FYI. At pi over 8, it's going to be, instead of positive 1, it's going to be negative, and then it'll be negative 3. And so then this one looks kind of like that. And then it's easy for us. Let's draw in 2 more periods. And if you're taking an exam, 1, 2, 3, 4, you would want to fill the graph. So maybe we'll do that on this one. Fill the graph. So I can get another asymptote on there. Oop. There we go. And out the other way, 1, 2, 3, 4. And then another one here. And then I'll just slip on my key points. In the middle, there's 0. And then halfway this way, it's at 3. And then, oh, and then negative 3. And 3. Negative 3. 3. Negative 3. 3. And negative 3. And I'm going to say my graph here is good enough that I'm going to make it into an infinite cloner for myself. And then I can just keep dragging those around and have all of them. And I'm sure you're doing an excellent job of graphing them yourself. And really, you know, you want to have the sense of drawing these. So watching me draw them is not as good as drawing them yourself. So do take the time to draw those as you go. So that's the tangent. We'll go a little faster on cotangent. So the graph of cotangent is next. And, you know, it has similar features. It's going to have asymptotes, but now the cotangent is cosine over sine. And so that's going to have asymptotes at different spots. So for this one, um, y is equal to cotangent x, which is cosine x over sine x. And this time we want to think about when the sine of x is equal to 0. And I'll just use a unit circle to kind of remind us of that. And if you remember this point, which would be maybe 1, 0, and these are cosine x, sine x. So since the sine is on the bottom here, and this is the angle of 0. So there, it's undefined at 0. And then if we go all the way around here, we'll be at pi, and this is negative 1, 0. And so that sine is 0 there, and that's at pi. I think I said negative pi, but if we came the other way as well, at negative pi, it would also be undefined. So this one is going to have asymptotes, asymptotes at x equals, and I'm going to go dot, 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 negative pi, 0, pi, 2 pi, dot, dot, dot. And so the beginning is going to be when bx minus c equals 0. And the end is going to be, and that is also going to have asymptotes at the beginning and the end. And the end is going to be when that bx minus c is equal to pi. Because this is also going to be that the asymptotes are going to be at x equals n pi. Sometimes I like to think of that as x equals 0 plus n pi, because, you know, I like to kind of list in my head that first one. You don't have to list it, but it just helps me to remember kind of what that looks like as I'm going through it. And then let's do our good graph of this one. And so this is y equals the cotangent of x. And so we have y equals the cotangent x. And the period is going to be pi. The domain is going to be like that other domain. So set of all x such that x does not equal, this is going to be pi n, or 0 plus pi n, comma, where x is an element of the real numbers and n is an element of the integers z, as we look at that. And then our range is from negative infinity to infinity. And this time it is also symmetric with respect to the origin, symmetric with respect to the origin. And our asymptotes are going to be when our asymptotes are going to be when x equals 0 and when x equals pi. And so let's do some numbering here, and we're just going to do one period. So there's 0, 1, 2, 3, 4. There's pi. And we'll just go up 2 boxes again for 1 and negative 1. And now we'll put our asymptotes there. One is on the axis. I kind of offset it a little bit so that I can kind of see it a little better. One is right there. And then this one, we have in the middle, we have our 0 again. But this time, when we're halfway between the first asymptote and that 0, we'll be at +1 for that one. And then here, we're going to be at -1. And kind of think about why that is as we go. And then I'm just going to sketch that in for us. And there it is. And so take a few minutes, draw that if you need to. And this concludes part 1 of Notes for 4-6. Have an awesome rest of your day.